Hello ladies and gentlemen, and welcome to the presentation of my doctoral project. Since this is the first time I participate at the CM's conference, I want to introduce myself real quick. My name is Ilja Shmelkin, I'm 26 years old and currently living in Germany. I graduated from the Technical University of Dresden in computer science and have a strong background in networks administration, infrastructures and recently education software research. Right after graduating in late 2019, I started my PhD project at the Chair of Computer Networks of the TU Dresden. My work there is funded by the German Research Foundation through a research training group for role-oriented software infrastructures for continuous context-sensitive systems. Imagine a simple client-server architecture in which a client requests a website from a server. In theory, this is a very straightforward process without any common points of failure. In the real world, however, a sudden increase in popularity of the website can cause long latencies, delays, or even failure to answer the client's request, because the server simply cannot keep up with the resource demand. What can we do about this? We can replicate the web server's content to more servers or virtual machines, and use a proxy load balancer to distribute requests among the web servers. Great, but also expensive. Every server that we create to process the big load of requests is useless when the sudden demand vanishes as fast as it appeared initially. Of course, we can just reduce the amount of servers manually, but this process is time-consuming and not efficient. Ideally, we want our server infrastructure to be resilient to failures of any kind and be dynamic in its size. It should provide minimal downtimes and be as cost-effective as possible. In 2009, Cheng and others introduced an infrastructure based on the Rainbow framework that can manage the amount of servers and the content that is provided in a self-adaptive manner. This process can be described as follows. Using the MAPE control loop, we first monitor the CPU usage of each web server individually. An analysis component then checks whether a predefined threshold is surpassed and decides if the infrastructure has to be adapted. A planning component reacts on this decision by creating a suitable adaptation plan that includes commands to increase or decrease the number of virtual machines with web server software. One or multiple execution components then execute this adaptation plan by actually adding or removing virtual servers. The power of self-adaptivity added through control loops like MAPE or MAPE-K is of course much higher than shown in the simplest scenario, but it is also much more complicated. In my PhD project, I want to address several open fields around the self-adaptive MAPE control loop by mainly focusing on the monitoring component and the communication between multiple components or even multiple control loops. Before I go into further detail, I want to quickly introduce an interesting definition on which my work is based. As infrastructures can be very different in size, shape and complexity, Weyns and others released theoretical work on MAPE-Patterns in 2013, which is a simple graphical notion for describing systems with multiple MAPE control loops and how the individual MAPE components interact with each other regarding control decisions. A pattern is a graphical representation that can be either abstract or concrete, as depicted in the slides. The abstract pattern describes groups of MAPE components and how they interact with an underlying managed subsystem. In the previous example, the managed subsystem can be the web server software or the load balancer, for example. The concrete representation of the pattern is one specific configuration for a particular self-adaptive system. MAPE was originally designed as a hierarchical approach, where each level of hierarchy contains instances of all MAPE components. With these patterns, a much finer definition is possible, which is why I use them as a baseline for my work. From this point, my goal is to answer, if possible, all of these questions. As I told you before, my main focus is monitoring and communication. When we talk about monitoring, a fitting metric format that describes the system is crucial. Since there is currently no definition of which metrics a self-adaptive system should expose, I want to conduct research on what metrics are useful and in which format we should represent them. The goal is to create a fitting metric representation standard for self-adaptive systems. Monitoring can be done on various levels of complexity. Imagine you gather simple metrics in a key-value manner and use each individual metric to drive conclusions about your system's state. This can be very useful, but even more powerful would it be to analyze linear metric correlations by calculating pairwise dependencies between metrics, which, of course, is very resource demanding and therefore has to be done in a very intelligent way. Therefore, I want to find good trade-offs of how to calculate linear and even non-linear relations during runtime. Next, in the community of self-adaptive systems, no standardized way of data communication is defined yet. Before I can even think of transporting metrics over the network, in distributed control loops, I have to figure out a standardized way of encoding, transporting, and decoding data within and across control loops. One of the main contributions of my PhD project therefore will be a definition of interfaces and best practice communication protocols for self-adaptive systems in the context of control loops. Finally, if we think of decentralized and distributed self-adaptive systems with multiple monitoring components across the network, is it necessary to replicate the data of each monitoring component to find a global fitting adaptation decision, or is it sufficient to use partial replication or even use no replication at all in some cases? I strongly think that a system's performance can be enhanced by not following the full logical sequence of the MAPE loop in every case, but using already gained knowledge to speed up the adaptation process. Since monitored data is a big part of the knowledge we have about a system, I want to research the performance enhancement potential of the monitoring component. Before I end my presentation, I want to give you a short insight about what I've done so far after submitting my doctoral paper to the CMS committee. The information that I will present now is work in progress. However, a contribution on this topic will be ready for submission by the end of August. To create protocol standardization recommendations, I first tried to precisely define which data has to be transmitted in local, distributed, and decentralized control loops between each individual MAPE component. As you can see now, a pretty specific definition is possible, as each component has a limited amount of possible interfaces. Note that I also considered a knowledge repository, which aims to save relevant data throughout every control loop iteration. Currently, I can distinguish either push or pull operations for one of each of the following data types: large volume metric data from the managed subsystem and between monitoring components. In the web server scenario, the monitored data can be the CPU load of each web server, the number of active virtual servers, or which type of content they provide. Next, medium volume query results between analysis components and monitoring components. The communicated data could be the mentioned metrics aggregated for a specific time window, which is representative enough to decide if the web server infrastructure needs to be adapted. In theory, the adaptation decision can then be negotiated between analysis components in scenarios where multiple analysis components exist. Next, the analysis component communicates the prior calculated decision and additional data like the average CPU load of the whole infrastructure to the planning component. Multiple planning components could then negotiate for a suitable adaptation plan. The adaptation plan then is communicated to the execution environments. Next, vendor and operation system specific communication happens when functions and operations get executed by the execution environments. The data can span logging, error messages, or negotiation between execution environments. Finally, every component can communicate meaningful results or data to the knowledge repository. The knowledge repository then aims to organize the data in a meaningful way. When we specifically name those interfaces, as you can see now in the slides, in the next step we can compare different communication protocols. With version 3 of the Simple Network Management Protocol, additional security and authentication was added. Paired with its low complexity, lightweight setup, and widespread acceptance in the network management community, it is a very fitting protocol to be used in communication scenarios like the one I described before. Therefore, I started using the SNMP protocol for each of the interfaces. I recreated a self-adaptive web server infrastructure, which was introduced by Mr. Cheng and others in 2009, and as you can see in the slides now, ran multiple performance tests peaking in 12,000 requests per second, which are created by a cluster of 6 benchmarking machines. Other than Mr. Cheng, I did not use the Rainbow framework, but a more generic approach of the MAPE control loop with a focus on SNMP as a communication protocol. The conclusion was that SNMP is a suitable communication protocol when referring to performance. However, in the upcoming contribution, I considered many more parameters of SNMP. In the slides, you can see now how an infrastructure with a total number of 4 web servers adapts to only use as many servers as needed by enabling them one after another if a resource demand threshold is surpassed. I wish you and your families the very best in this for us all new situation. Thank you for joining my presentation. On my last slide, I want to show you all of my currently planned milestones until I will submit my PhD thesis in September 2022. Please note that I included my email contact at the bottom of the slide. If you are interested in my work or have any questions regarding my presentation, I would be happy if you contact me via email on ilja.shmelkin@tu-dresden.de.